of the particular fin or at particular point, as well as the heat transfer. Okay. However, okay, if you look to the textbook, okay, where is it? In the, yeah, just after the case number 4. So if you look to this paragraph, yeah, this one, the solution of general fin equation for the case of convection from the fin tip, because this is the closest one that replicate the real condition. So they need to use we need to use a more simple equation, okay, and then practical as well as. So for this reason, they introduce new parameter that call corrected fin length, and this corrected fin length, okay, will be used to calculate the fin efficiency and the fin performance. Okay, I can say that this is a fin performance. Okay, I will explain again in the slide after this. Okay, so the fin efficiency topic, okay, is part of the topic in the extended surface. Okay, introduce because of we want to calculate the heat transfer, but in a more simple manner, in a more simple equation. Okay, so if we know the fin efficiency, okay, normally we can calculate the heat transfer. Okay, so what is the efficiency? What is the common terms that efficiency? So normally efficiency, any efficiency, okay, is equal to the output divided by input. This is the common that you may use previously, or sometimes we put it actual divided by ideal. Okay, how good the system perform. Okay, so same goes to this fin. Okay, so we can calculate the fin efficiency if we know the actual heat transfer divided by ideal heat transfer, meaning ideal is the maximum value of heat transfer. Okay, so then we can get the fin efficiency. Okay, but in most cases we don't know the fin actual. Okay, we can calculate fin maximum, okay, and we can calculate fin efficiency based on the geometry of the fin. Normally, fin efficiency is a function of fin geometry. Okay, so we need another equation of fin efficiency. Okay, and how about maximum? Okay, so this is the fin maximum equation. This equation is same like the convection equation, Q equals to H A delta T. Okay, so this is convection equation. Okay, so in this case, the efficiency only occur if your temperature across the fin is the same. Meaning if this base temperature is 80 degrees Celsius, so the maximum that the fin will be reached is when the fin also in the same temperature. this is a base temperature. Okay, but this is the fin temperature at whether x0, x quarter, x half, x quarter half, or x equals to total length. Okay, this is the maximum condition. Okay, but in actual, you will get the temperature like this. The temperature will be reduced as the location far from the base. Okay, so if we can get this temperature, we can get Q actual. But if we can use the same temperature as a base temperature, this is a Q maximum. Okay, so normally we can estimate this, and we can estimate the fin efficiency using the fin geometry. I will show it later. So by knowing these two, so you can find Q fin in actual, okay, equals to efficiency of the fin times the Q fin maximum. Okay, so this is the reason why you learn about fin efficiency. Okay, is used to calculate actual heat transfer without using this long equation. Otherwise, you have to use this one. Okay, you have to use this long equation. This one. Okay, so this one, whatever you calculate using the yesterday equation, so this is equals to Q actual. Okay, so well, you can use this, but still there is some difficulty in order to find the M value, to find the hyperbolic function, and then you have to do some quite a longer equation, and chances to do a careless issue, I mean, you miss the calculation is a bit high compared to using this very simple equation. Q fin actual equals to fin efficiency times fin maximum. Okay, so how to find the fin efficiency? Okay, how to find fin efficiency? Okay, I think in your textbook, okay, there is some table. This table is very useful. In fact, this table is, I believe, if you are working in the company that design the fin, sure, you will use this table as well. You will use this table again. Okay, so look how they should indicate the fin efficiency of fin shape or fin geometry. Okay, so you only can get this if you know the geometry of the fin. Okay, so what is the this is tangent hyperbolic. What is M? M is a 2hkt. What is H? H is convection coefficient. K is thermal conductivity of that particular fin. T is the thickness. Okay, LC, remember LC, what is LC? LC is the corrected length. Corrected length that required in order to assume that it is probably exposed to the convection equation, convection condition. Okay, and from here you can calculate fin area. Okay, so same goes when you have a straight triangular fin. Okay, what is this? M is this value. What is L? L is the length of the fin. What is I1 and I0? I1 and I0 is a Bessel function. Okay, you need to go to this next table. Yeah, this one. This is the I1, I0 function. Okay, you need to define what is the egg value. Then this is your Bessel function for I0 or I1, depending on what condition that you want to calculate. Okay, so same goes for the next geometry, straight parabolic fin. Okay, circular fin. So they have their own fin efficiency calculation. Okay, this one is a bit complex. Okay, there is a Bessel function as well as I and K. Where you can get the K value? Here. This is Bessel function for the first kind and Bessel function for the second kind. Okay, so this is more advanced. I think I believe you learned this in the engineering mathematics. Okay, and then this efficiency. So same goes here and this one as well. Okay. In my point of view, okay, normally the fins will be used either. This is what I experienced in the industry or in the example of your problem. The common type of the fin is this shape. Okay. Also this shape and this shape. Sometimes you may have this kind of shape. Okay, but I don't think this will be asked during a test or final exam, because it will take quite a long time to calculate this one. Okay, because you have how many Bessel function? 1, 2, 3, 4. Okay, M is here, R is just the calculation of radius, equivalent radius. Okay, and the constant of C2. Okay, the rest is not very common. It's quite difficult. It's quite not common that you use this kind of straight parabolic fin, even though there is a possibility that the fin will be shaped like this. Okay, so this is where you can get the fin efficiency. So back to the calculation. So you can get the fin actual heat transfer if you know the fin efficiency and the maximum fin value from this equation. Okay. So if you look in detail how to calculate the fin maximum, so you need a H value, where the H value is the heat convection coefficient of the surrounding. Okay, normally normally given in the problem, or you need to define from the convection coefficient correlation. Okay, the H value. A fin. What is the A fin? A fin is normally the area of the top fin, the front, and the bottom one. Okay, so it is not considering this. This one they are not really considered. Why? Because of the corrected length already consider this shape, or somehow you may check the area of this tree is more significant compared to this area. Okay, if I can draw this in different color. So this area and this area probably not significant compared to the area of the blue sheet. Okay, so that is a A fin. But don't worry, if you're not really sure how to calculate A fin, the A fin is given in the table. See here, this is the A fin, area of the fin, the effective area of the fin. Okay, is given already in the table. So that's why I say this table is quite important for you. Okay. And then the TB is the base temperature. The T infinity is your T surrounding. Okay. So if you need to calculate the AB is the area of the base. This means area of the fin base if the fin is not attached in the body of the system, body of the object that you want to release the heat. Okay. Okay, so once you know the maximum maximum heat transfer, okay, this one, so you can find the actual fin if you know the fin efficiency. Okay, so this is how they used to calculate the heat transfer actual by fin. So you don't use all the tangent hyperbolic, sinus hyperbolic function to calculate the heat transfer. Okay, whether you are dealing with the long fin or this is another equation of long fin and adiabatic. I mean, this one is to show how they got this fin efficiency in case of long fin. Okay, because if you look here, this equation equals to 1 over ml. This is not available in the table. Because why? Because this table is considering for case number 4. Sorry, case number, this is tangent hyperbolic function, ml. Because in this case, this is for the, might say this is for the case for assumption. Okay, so when you say that the fin tip is exposed to the convection coefficient or convection condition, then you can use this efficiency calculation. Okay, so again, with that equation tables, so we need to understand or we need to calculate the corrected fin length. So what is the corrected fin length? This corrected fin length is the length that we consider the effect of convection in on the tip of the fin. Okay, on the tip of the fins. So at which you will not consider anymore the L value. Okay, so you now have the new value of L, which is symbol as LC, is a corrected fin length, where this corrected fin length is considered the value of the cross section, okay, and the perimeter of the fin shape. Okay, so AC is the cross section of the fin, and P is the perimeter. Okay, so P here is the perimeter of the fin cross section. Perimeter of fin. Okay, so in fact it is given in the table as well. Okay, here and also here. Okay, not all actually fin geometry have LC. Okay, only the simple one like a rectangle shape and the rectangle. This one is a pin fin shape. Okay. Okay, that is using equation. Okay. There is another way to calculate the fin efficiency, but using graph. Okay. So I can say that so one method, okay, so first method to calculate fin efficiency is using table 3.3, okay, equation. Okay, so another method to calculate efficiency is using graph. Okay, meaning that you have this graph. Okay, I think in the textbook they give you, yeah, this one, graph 343, graph 344. Yeah, only these two. Okay, 343 and 344. Okay, so graph 3.43 and 3.44. Okay, so just you need to use this graph, okay, without involving a lot of calculation related to the M, related to the area and so on. Okay, but the reason I don't not like the calculation using a graph, because the value is approximate, because you not get the accurate value compared to you are using the equation. So I can say that the answer will be approximate. So how to calculate the efficiency? First, you need to find this value. What is the symbol means? Is it zeta, or I think this value, where you need to know the corrected length to the power of 3/2, H value, K thermal conductivity, AP. What is AP? Is the AP equals to LC over T. Sorry, LC times T. Okay. So when you got this value from the fin, then let's say you get, let's say from one calculation for the rectangular fin, so you got this value equals to 1.5. Okay, so what you need to do, you find the 1.5 value, do some extrapolation to the graph. So this is the cross section, so you get the value of efficiency at 0.4. Okay, using graph 3.43. So this is fin. Okay, so you can get directly, but like I say, the value that you try to estimate is from the approximation method. Okay, so if you have a difficulty to find some value, let's say you got 1.3, so which is okay, 1.3 should be okay. Let's say 1.35, for example. So you're not sure whether the value, whether it is more to the left or more to the right, then you get some uncertainty in your calculation. Okay, but this is more some people say this is more faster than the equation. Okay, but it's up to you whether you can use the table or you can use the graph. Okay, so this is another graph 344 for the annular fin. Okay, this is the table of 343 that I mentioned just now. Okay, so that is a fin efficiency calculation. Okay, because from the fin efficiency you can calculate the heat transfer value of the fin. Okay, So next one, we need to calculate the fin effectiveness. Okay, so how to calculate the next? Okay, the next fin performance parameter is a fin effectiveness. Okay, I might say that there is two fin performance parameter. One is a fin efficiency. Okay, so fins, I can open a blank A4. Okay, so fin performance parameter, okay, can be divided into two value. One is a fin efficiency, another one is a fin effectiveness. Okay, so what is the fin efficiency just now? Efficiency of the fin equals to Q actual of the fin divided by Q maximum of the fin. Okay, and how about the effectiveness? The symbol is the epsilon. Okay, so what is the fin effectiveness? Heat transfer fin, okay, heat transfer of the fin divided by heat transfer without fin. Okay, so we can say that this is the effectiveness. Heat transfer actual fin divided by heat transfer without fin. Okay, so look to this image. Okay, heat transfer by the fin, which is actual, divided by heat transfer without fin. We want to know whether how good the fin can release the heat with and without. Okay, so in this case, you need to calculate the heat transfer. Q fin you can get from the previous calculation in the fin efficiency, or you make of hyperbolic function, and you need to calculate the heat transfer without fin. Okay, which is HAB. This is AB is the base area. Okay, like this. You imagine this this image in the left. Sorry, in the right. So this is object without fin. This is object with fin. Okay, so with fin you have this component, okay, attached to the object. But if we get rid, if we don't have the fin, we only remaining the base area. So this base area is your reference in order to calculate what is the heat transfer if the fin is not available in that particular area. Okay, so well, the equation is only this. Okay, so you can calculate the fin effectiveness on every single geometry of the fin. Okay, this is a long fin. They're using the original equation and they got this kind of terms. But for me, the important thing is you can find the fin effectiveness once you can calculate the heat transfer of the fin in actual. Okay, and the heat transfer without the fin. That's all. Okay, this one is just to compare how to look the calculation if the condition is different from the convection case. Okay, this is a calculation if you are dealing with fin with multiple number of the fin. Remember in the previous sample, you only consider single fin. Okay, so what happens if you have more than single shape? Okay, like this you have how many? 1, 2, 3. Okay, so how you want to consider this? So you have to calculate the area heat transfer where the fin is considered and where is the fin is not available. Meaning this is the area of the unfin, this one, and this is the area of where you have the fin. Okay, this one and the bottom one. Okay, so the area of the unfin is not only in here, same goes to here, here, okay, as well as the bottom one. Okay, the bottom one. So that's why you need, normally what they calculate first, they only consider one side, and then they will multiply by how many that this fin will be replicate depending on the height of the object or the wall that you want to attach the fin. Okay, this one for a single single section. Okay, how can I say this is a single section? Okay, so you have to consider heat transfer for the fin and heat transfer without fin, which is unfin. Then they say you are replicating this for about 10 times because you have a 10 fin, then all this calculation need to be multiplied by 10, for example. Okay. Then if you want to calculate the overall effectiveness, you can compare this only with one single case. Okay, so this one A unfin compared to the area of no fin. Where is the area is no fin? So if I can draw in the different color, let's say put the yellow one. So the area of the unfin is this one. Okay, so this one. Okay. Okay. So that is if you are dealing with multiple fin in one system that have multi fin assembly. Okay. Okay. This one is to this topics is used to design how long that the fin is required in order to sufficiently release the heat as desired by the system. Okay, so if we try to plot the temperature variation across the fin, okay, so if the fin is infinitely long fin, okay, so you may have this kind of temperature distribution, maximum at the beginning and then start to reduce until it become nearly zero and almost zero as the fin got very long fin. Okay, but of course we don't want to waste the component that at which there is no more heat transfer. So we need to find what is the maximum value of fin length in order to sufficiently use to release the heat. Okay, so using the actual heat transfer calculation and heat transfer at using the long fins, so you can use this to define the value of suitable length or proper length of the fin in order to release the heat for one particular fin geometry, okay, which is tangent hyperbolic ML. Okay, what is the M? M is your fin parameter to HPKAC. Sorry, this one is a, in general is a H convection coefficient times the perimeter divided by thermal conductivity divided by cross section of the fin. Okay, or if you know the fin shape, then you can use the table of calculation M here. Okay, but if you use the general value of the M, then you can use this where is the general equation M? Yeah, this one. Okay, okay, that is the, I can say is a fin parameter calculation. Okay, any question? Okay, okay, let's we do some example here. If you have any question, you can write down in the chat box. Okay, okay, this is example how we can use the fin efficiency in order to calculate the heat transfer of the fin. Okay, so this is a rectangular fin. Okay, attached to the plane wall with a surface temperature of 350 degrees Celsius. Okay, so meaning the base temperature is 350 degrees Celsius. Okay, attached with a straight rectangular fin. Straight rectangular fin. Okay, so they not mention the material, but they give you the value of thermal conductivity 235 watt per meter Kelvin. Okay, and then this fin is exposed to the ambient air, so this means the surrounding air at 25 degrees Celsius. Okay, this one, and the convection heat transfer coefficient is 154 watt per meter squared Kelvin, meaning this is the H value. Okay, okay, seems that there is many fin, but they only ask you to calculate one single fin. Each fin has a length of 50 millimeter, so this means the L is 50 millimeter. The base of the fin is 5 millimeter thick, this one. Okay, this is the length, this is the thick, and the width of the width of the fin is a 100 millimeter. So you have all the geometry of the fin. Okay, so determine the efficiency. Okay, so first you need to find the fin efficiency. Okay, second you need to find the heat transfer rate, which is Q dot fin. Okay, because it's just heat transfer rate, so this is the actual one. Okay, it's not ideal or maximum. And number three, they ask you to calculate effectiveness of the fin. Okay, so basically you will use in fact this problem asks you to use two methods of each fin using A, table, B, figure. So this means you have to solve this using two methods. Okay, so first A, you need to use table of the fin. Okay, table 3.3. Is it the table 3.3 there? Yes, table 3.3. Okay, this one, table 3.3. Okay, and second one, you need to use, you need to repeat the calculation, but using figure 3.43. Why? Because in 3.43, you have same geometry as given in your problem. Okay. Okay, so how to start this? Okay, so normally this problem, okay, for information, I'm still checking your assignment 1. Okay, some of you did not follow the, some of you, okay, follow the right, follow the instruction properly. Meaning my instruction is you should have, for in particular solution, okay, of a problem, so you should have first the schematic, okay, and then next one you should have the properties. Sorry, I think this assumption first. Assumption, okay, and then the properties or thermal properties. Number 4, you should have the analysis, okay, and probably the last one is a discussion. Okay, some of you properly written this step, which is good, but some of you, I don't know, probably you just putting all the information in one section. Okay, and sometimes I cannot find the assumption written, and also the properties is not mentioned in the clear way. Okay, so you may say that, oh, everyone know this, but whenever you, believe me, when you are going outside, when you are working outside, okay, as a engineer, to show to the whether your boss or whether your clients or whether your um, um, stakeholder, okay, so you need this all information, because this information will be asked by them. Okay, they will want to know how, what is the assumption that you putting in order you use this analysis. Okay, of course this one is very simple in our case, but when you are dealing with a more complex problems, okay, so this step is very useful in order to give understanding to those who are not really in the mechanical background, for example. Okay, because let's say you want to show this to your clients, okay, probably your client is a civil engineering background, so they want to know what is your schematic, what is your assumption, what is the properties involved, even though the properties already there mentioned, but you need to uh, state it again in your solution um, step. Okay, okay, so back to this problem. So first you need to draw um, the schematic. Okay, in fact, cannot, how to, so the schematic will be, you need to draw again the fin. Originally, if you, I'm not sure in the exercise, is it given the figure? Oh yes, it's given. But normally in actual case, so they not give you the schematic, that you have to draw the schematic. Sorry for my sketching, it is out of control to draw in the digital way, so forgive me for the bad handwriting. Okay, so this is your thickness, this is your width, this is your value of the L. Okay, and then the surrounding temperature is about 25 degrees Celsius. We have the H value of 154 watt per, sorry, 154 watt per meter squared Kelvin. Okay, and then you have this all value. L is 50 millimeter. W is the width, 100 millimeter. The thickness. Of course, in your test, sometimes you have a very time constraint, very short time. So just draw the important parameter, important sketch and important parameter that useful in your calculation. But for your assignment, of course, you got a plenty of time, so you can draw your schematic properly. Okay, complete with the information given. Okay, what else? Base temperature at 350 degrees Celsius. Okay, yes, and the K value of the pin is a 235 watt per meter Kelvin. Okay, so you can, okay, so this is the schematic that you want to put in the what information that you need to put in your schematic. The next one is your assumption. Okay, so what kind of assumption that required in this case? Okay, so since, okay, from the problem, okay, whether the problem said anything, a plain wall with a surface temperature, okay, if we are exposed to the, okay, so this case normally we are using steady state condition. Okay, because they not said that there is a variation of time, so we can assume that the condition here is a steady state condition. Okay, steady state condition of the value of temperature, value of convection coefficient. Okay, because normally this temperature, this value of H, okay, if we check carefully, if we check in actual way, it is fluctuate as the times change. Okay, but for this case, to simplify the analysis, we said it is a constant, it's a fixed, so it's a steady state condition. Second, you can say that because we are dealing with some properties here, so the constant properties of thermal conductivity, okay, of K value. You need to write down thermal conductivity. Okay, because otherwise the K value will be changed, because you may say that this material is not isotropic, it's not homogeneous. But with this kind of assumption, we can say that the K value is a constant regardless of any point, whether the point here, whether the point here, whether the point here, or in the center, or in the middle, or in the other side of that particular fin is still 235 watt per meter Kelvin. Okay, what else assumption? Okay, because there is a temperature here, suppose if there is a temperature here, you should consider radiation. Okay, because radiation occur when the temperature of the surface or object above 0 Kelvin. Of course, this is above 0 Kelvin, but we don't consider. Okay, so we say that neglect the heat by radiation. Okay. Okay, what else? I think there is other assumption. Okay, if you look in the textbook, okay, other assumption that can use is one-dimensional. Okay, one-dimensional analysis. This is one-dimensional analysis. We not really cover two-dimensional or three-dimensional. Okay, and then you can see that the heat transfer coefficient is a constant. Like I say, the H value can be changed when you vary with the time. Okay, the H value can change. So to simplify that, we assume that the H value is a constant. Okay. Okay, that's all we can put in the assumption. Okay, the properties. The only properties given here is the thermal conductivities. Okay, the K value of the fin. Okay, the thermal conductivity of the fin, thermal conductivities of the fin, okay, is 235 watt per meter Kelvin, and is assumed constant. Okay. This assumed constant is not compulsory, but just to give you more understand that this value will be constant throughout your analysis. Okay. Okay. The lengthy part, analysis. Okay. So the first three steps is just a very short one. In fact, you just reword what have been stated in the problems. Okay. So the fourth part, which is analysis, is a bit lengthy depending on your analysis. Okay. So this problem you need to solve using a table and figure. Okay. So let's say I put here analysis. Okay. Analysis stage. Okay. So using this information given, okay, so first we need to use a table. So you open the tables, this one, this table. Okay, if I can so you may use only this, okay, geometry. It's a straight rectangular fin that you need to consider for your calculation. Okay. So this is a straight rectangular fin. Okay. So you need to calculate M value, LC value, and fin area. Okay. And you can get the fin efficiency. In fact, the first question is the fin efficiency. So you can calculate this first. Okay. So how to? Okay, I also not remember this equation. Okay. So that's why this is the reason why this course is open book, because there is so many equation, and I believe no one can remember the equation. So I put it in the side by side so that we can write down what equation that we can use for the calculation. Okay, can you see clearly? Okay, so first you need to calculate the m value. Okay, so using table 3.3 for rectangular fin, okay, straight rectangular fin, so you need to find the m value, which is 2h over kt, okay, and then you need to find the LC, the corrected length for that particular fin, L plus the thickness divided by 2, and the area of the fin, okay, which is 2 times the width times the LC. Okay, so once you can get this value, okay, in fact this is the first question, right? They ask you to calculate the fin efficiency. So once you can calculate this, okay, so you can calculate fin efficiency equals to tangent hyperbolic if you multiply m with L, okay, sorry, LC divided by m LC. Okay, again, don't forget, this is, if you look to this equation, okay, if you look to this equation in the table, student always carelessly do this mistake. In fact, the equation also is a bit confused. The tangent hyperbolic is for the MLC, not only M. So what your previous friends do, or your senior do, is they calculate the tangent hyperbolic for the M first, then they multiply by LC. It's totally wrong. And you will get a different answer. So the MLC should be multiplied first, then you need to find the tangent hyperbolic value. Okay? Then divide by MLC. Okay? And your value should get below the, the value you will get between 1, 0. Okay? Between 0 to 1. Okay? It's a efficiency. Okay? So next one, when you finish the fin efficiency, then you can calculate the equation, the heat transfer. So you know that the actual fin is equals the fin efficiency from the first answer times the Q fin maximum. Okay, so this value when you calculate is equals to H A fin, okay, times this should be the so this should be the bigger bracket, okay, T B minus T surrounding. Okay, so the A fin you get from here, the base temperature is given, the T surrounding is given, and the fin is from the question answer number 1. Okay, and the last one, effectiveness. Effectiveness fin is equals, if you calculate, if you already calculate Q fin, which is the answer from number 2, divided by Q no fin. Okay, so this is a question answer number 2 divided by so you can imagine, so without this fin, so you only have HAB times base temperature minus surrounding temperature. Okay, you have this, you have this, you have this, but what is the AB? AB in this case is basically W times T. Okay, because this is the AB. Okay? At this section. Okay, at this section is AB, not here. AB is in here. So, but what I want to say is the area can be calculated if you know the width and the thickness. Okay, same H value and same for the temperature, then you can get the fin effectiveness. Okay. Okay, then you can compare your answer when you calculate using the figure 343. Okay, meanings for the 343, okay, you see this shape. I don't know whether it is clear or not, because I using two window here. Hopefully you can see quite clear. Okay, so first, okay, let's say for the figure, okay, second B, using figure or graph 3, 4, 3. Is it 3, 4, 3? Yes, 3, 4, 3. Okay, first you need to, for okay, you need to find the epsilon value. Epsilon, this is epsilon. Okay, seems like effectiveness. Don't confuse with effectiveness value. Okay, so find the so this I put a difference so that you're not really confused. LC to the power of 3 times over 2 times H over KAP to the power of half. Okay. Okay. So you have this LC from the original calculation, LC corrected length. You have the H value, you have the K, you have the AP. What is AP in this case? The AP is here, LC times T. Okay, AP equals to LC times T. Okay, so with this value, suppose you can get the value of what, zeta, epsilon. Okay, this symbol. Then you can say using, let's say you what you I'm not sure whether what the value you should get from the answer previously. You should get 0.59, okay, 0.6. Okay, so let's say you can get 0.6. Okay, so using graph 343 for rectangular fin shape, okay, the corresponding value, for epsilon equal to 0.6. So where is 0.6 here? So this is 0.6. You do some estimation. This is quite challenging. Okay, this is the rectangular shape. Okay, so the rectangular shape is represent this trend line. Okay, so the value probably how much you can say 0.82 or 0.81. I can say probably 0.82. Okay, so the value of efficiency here approximate, sorry, it should be in here. So the value approximate, where's my pen? Okay, 0.82, okay, or 82%. Okay, thank you, Aiman. Okay, so from this value, you extrapolate, and then you can get this efficiency value. Okay, so that's why let's say they ask you to use this figure, then graph in your solution. Okay, but like I say, I don't like to use graph because it's very crude, very approximate. So I'm prefer to use the table one. Okay, I think from the table, from the equation, if I'm not mistaken, the value, the answer for this is about how much? This one is about 0. This is, you can get very accurate 0.13. Okay, 0.13. Okay, if because I already give this exercise previously as assignment, so they got 0.13. But if you are using this one at 0.6, you will get close, approximate 0.82. Not very accurate, but a bit close to the value of using equation. Okay. So next, you need to repeat. Once you get the fins efficiency, then you repeat the same equation. Okay. This graph is just to assist you to calculate the efficiency. Once you know the efficiency, the next one to calculate the heat transfer, you still use the same equation. There is no heat transfer can get directly from this figure. Okay. So you still use N fin equals to Q fin maximum. Okay, and for the effectiveness, still you need to use the general equation for the fin effectiveness. Q fin divided by Q no fin. Okay. So the only difference between table and the figure is the method to calculate fin efficiency. The table is purely equation. Okay, purely equation with the assumption of corrected length. Okay, but the figure use the extrapolated value of fin parameter, I can say this is fin parameter because you can see here the M value is considered in this one, HPKAC. Okay, this is not really M value, but is some sort of M value embedded in these terms. I don't know in the textbook what is actually this zeta value called. If you look to the figure 343, they not mention they just say fin profile parameter. Okay, so there is no specific name of this symbol. Okay, so they just say that it's a fin profile parameter. Okay. Okay, any question? So this is example of one problem that asks you to calculate the fin efficiency, fin heat transfer, and the effectiveness. Any question, guys? So far, are you with me or you? So what I want to stress here is whenever you solve a problem, please solve it accordingly, step by step, so that you can understand. Okay, so how this value is come from and how the step is solved. Okay, in fact, if you go to the textbook, the information given is quite clear. Okay, where is the calculation of fin effectiveness, fin efficiency? Okay, this one. Okay, example 3.12. Okay, so they're using this fin parabolic fin. Okay, sorry, this is not fin, this is a fin. You know the difference between fin and fin? Fin is like additional component, same as across the width of the system, but the fin is like a component, a single component, like, how can I say, it's a pin shape. See, this is a pin shape. You can see here a pin shape. Okay, so this pin shape is quite common. Remember when I show you this image of a fin? Okay, this is a rectangular fin, this is angular fin. See, this is a fin shape, but you see how many how many pin fin is obtained here. You will not calculate all, but you only calculate once, and then you multiply by how many pin fin that you have in your system. Okay, because all the pin is a symmetry, unless you design a different way. Okay, this is, I think, I'm not sure whether this is due to the design or this is due to the picture that have different. But originally this is a pin fin shape. Okay, probably they just elongate the shape or the location, the position of the pin fin, like, so that it looks like this pattern. Okay, but originally it come from this shape, pin fin. Okay, so if you look to this pin fin, okay, problems in the example, so this pin fin is in parabolic profile. Okay, what meaning by parabolic profile? Have the large area in the beginning, in the base, and small area as you move to the towards to the fin tip. Okay, so what the calculation? Okay, they give you assumptions. Okay, they put you properties. In fact, originally they should draw the geometry, the diagram. Okay, first the diagram, second the assumption, and third the properties. Okay, and then the analysis. So see here, first they calculate the M value, and then they calculate the fin area, and then you can get the fin efficiency. But because of this pin parabolic profile, they will use this Bessel function. Because parabolic required a Bessel function. Bessel function used to estimate the parabolic's constant value. So where is the I1, I0 obtained? From this table. Okay, if you have a time, just go, where is it? Sorry, where is the parabolic function? Oh, I missed the table, is it? In the figure, yes, table 3.4, this one, modify Bessel function. Okay, used to evaluate for the parabolic profile, fin with parabolic profile, not linear function. If linear function, you can use the linear equation, but when you have a non-linear equation, then you have to use a Bessel function. Okay, so so you use fin efficiency, then you can get the value 0.96 or 96%. Okay, and next you calculate the actual heat transfer rate. Okay, and you can calculate the fin efficiency. Okay, okay guys, any question? So there is some discussion here. Okay, but discussion is just to say that the fin efficiency can be determined more accurately by avoiding the interpolation error by using equation. Well, this is more specific discussion related to the accuracy of the answer. Probably the discussions, what you can say, the discussion, if it is not relevant to your, if it is not require accuracy, then you can say that based on the single fin calculations, so the overall or the performance efficiency is 96.32%. We can say it again here in terms of percentage, 96.32%. Okay, and the effectiveness is 10.3 times better if the fin is not available. This means here 10.3. This means the effectiveness show that the heat transfer will improve 10.3 times 3.3. Okay, I put in words, times. Okay, if compare the system without fin. Okay, without fin will be improved 10.3 times if compare the system without fin. Okay, system will be improved 10 times. With the, you can reword this one. The heat transfer will be improved 10.3 times if compare the system without fin. Okay, so this is kind of discussion that you can put in your analysis, final analysis word. Okay, any question? We have about 30 minutes. Basically, we finish the chapter 3 because next one 3.7 here is not covered in your It's not covered for your syllabus, but if you want to read for additional knowledge, no problem. Okay, our topics for the chapter 3 is until here. Okay, until 3.6, until here. Okay, so if you look to the, is cover from first chapter 3.1 until 3.6. Okay. Okay. Any other question that you want to ask? Probably. Okay. I want to show you some example related to the long equation. Okay. If you look to the example in the back of the chapter, in the last page of the chapter, okay, you can check some example related to the general fin equation and fin that required analysis of efficiency and effectiveness. Okay, this is your exercise. Heat transfer from fin surface. Okay. So I'm not sure whether you are aware or not the type of the exercise in the textbook. Whenever the problem got C value, this is a concept question. Concept meaning your understanding. Okay. So this is not an analysis problem. Okay. C means conceptual question. So you can see here, there is a conceptual question about what is the definition, what is the different, can you explain about this condition? Okay, so all this until 326, 3126. Okay, so from 3126 is about derivation. Okay, you can check how they derive. Okay, like the example that we discussed in the class previously. Okay. Okay, this one, 317. If you look this example, okay, this is a pin fin, aluminium pin fin. It's just a fin. It should be a, yes, this image, okay, aluminium pin fin. Okay. Probably because they give you the, they already give you the figure, then you know that this is a pin type fin. Attached to the surface, if the heat transfer coefficient is a 12, so this value is a 12 watt per meter squared Kelvin, there is an error in the rate of heat transfer when the infinitely long fin assumption is used instead of adiabatic fin assumption calculation considered. So this means they ask you to calculate the heat transfer, the rate of heat transfer. So Q fin, first when you use long fin equation, and then you need to compare versus Q fin for the adiabatic. Adiabatic. Adiabatic means you neglect the fin, the heat transfer at the fin tip. So which equation that you want to use? So you can go back to the equation. Where is the equation? There is 4. Okay, this one. So which one? So you need to compare Q fin from this condition, number 1, compared to this one. Q fin for the negligible heat loss. Mean this is a at fin tip. Okay, so you need to compare what the value of this compared to the what value of this. Okay, of course the infinite long fin is the more the simplest one, but suspect to the large error. So you need to compare this. So you have to use the long equation for the long fin and long equation for the adiabatic fin, and then compare the value. Okay. Okay, let's say you want to do this example, 3, 1 to 8. Consider a very long rectangular fin attached to a flat surface. Okay, they're giving you all the information. So what assumption that you want to use for this? What case that you want to use this? Okay. So if you look to this example, consider a very long rectangular fin attached to a flat surface such that the temperature at the end of the fin is essentially that of surrounding air 20 degrees Celsius. So this means the end of the fin is essentially or close to the 20 degrees Celsius. See the wording here? A very long rectangular fin. So you can use the case number 1. So use the equation which is a very long rectangular fin, infinitely long fin. Okay. So use this equation to estimate the heat rate, the heat loss, as well as the fin temperature at distance 5 cm. Okay, meaning you need to calculate T temperature fin at x equals to 5 cm. Okay, 5 cm, which is if the total length is 10 cm, this is a L over 2. Okay, so again you have to use the equation of temperature distribution. Okay, so same goes to the other. So you need to read carefully. So at which you need to define this problem represent what case, whether it is case 1, case 2, case 3, as case 4. Okay, or otherwise if it's not mentioned, then you can use the fin performance calculation. Okay. This is quite interesting example because this is more actual fin. I think you need to assume you need to assume that this fin is represent which simple geometry that represent this shape. Okay, a turbine blade made of metal alloy, and then the turbine blade is exposed to the room temperature. The base determine the heat transfer rate, and the tip is adiabatic. Determine the heat transfer rate to the turbine blade and the temperature at the tips. What do you think? This one represent what shape? Oh, in fact, they don't use. They already give you the information, length, the perimeter. So they already give you L. This is a P. This is cross sectional area A fin. So they already give you all the information directly. You just use. Okay. You need to choose either of these 4. Okay. Here the base adiabatic. See, this is the keyword. The tip is adiabatic. Okay. The adiabatics mean you need to this one. Okay, negligible heat loss. Okay, so this meanings at the tip, negligible heat loss. Okay, case number 2. Okay, this one you cannot do. Okay, CNS meaning you have to use some computing programming, okay, in order to solve this one. So you can avoid this example or this exercise to exercise your understanding. Okay. But some problem you cannot solve it because it is in the different units. Okay, try to take example that use SI unit, okay, like this, okay, they use the SI unit. If involving English unit, where you have this symbol E, E meanings the symbol or the unit that used in the problem is English unit. English is imperial. You have the what? The what is BTU? BTU is pound per pound weight, pound force. Okay. H is hours, feet is feet instead of meter. They are using feet instead of Celsius. They are using a Fahrenheit. Okay. Instead of millimeter or meter, they use a inch. Okay. So you can use this, but you need to familiar with the English unit. So try to do the English unit first. Sorry, the SI unit first, and then if you still want to do, then go ahead. You can do the English unit. No problem. It's just the same procedure, but only different unit. Okay, guys. There is many example. This is example that we just do it now. Okay, you can try as your exercise. In fact, I will take one or two exercise from here to be a part of our assignment. Okay. Okay. I think any question so far? So if not, I think I will stop here. I will stop here. I believe that you can get a good understanding of the how the conduction analysis will be done or performed, okay, by using from the simple system like a plane wall, and then cylindrical, and then spherical, and lastly to the application of the extended surface or fin. Okay, so if you look carefully that most of our example dimensional analysis. So of course the correct one is if you can deal with a 2-dimensional or 3-dimensional, but because of we have some limitation, then we limit our analysis only for the 1-dimensional. This is a part of your assumption. The analysis that you do here is a 1-dimensional analysis. Okay, so so with that, I think that's all for today. Okay, thank you very much for your attention, and I will see you again in the next week's class with the new topics. Okay, check with the e-learning, the kid, the lecture note. If not, I will remind me. I will attach the lecture note for your reading before the class. Okay, guys. With that, thank you very much. Assalamualaikum warahmatullahi wabarakatuh, and good day to everyone.
Thank you, Doctor.
Okay, Doctor.
Thank you, sir.